Okay, are you guys ready for mesh current in phasor domain? So here we go, a little circuit, some notation stuff. This is an AC circuit, but they're giving it a polarity here, which in this case doesn't really matter, but in some circuits it does, and we'll see that in the next chapter. So this is a sinusoidal voltage signal, 170 angle 0 degrees, giving us a phasor, and this is volts. Okay, this is RMS. So that's, I'm going to put a bunch of arrows and stuff. That's kind of important. So this 170 is an RMS value, not the peak value. And remember, RMS values, their whole point is to make power calculations easier in AC circuits. At least that's the way I think of them. So here's a little guy. They've already put it in phasor domain. So this is minus J20 and this is J16 ohms, 12 ohms, 10 ohms. Okay, they've already put this in, everything's in phasor already. And they're asking us to find the complex power S phasor, and which really sort of means you're going to have to find P, which they're asking us for. That's the real power P, and then the reactive power Q. And then they're asking us to do a power balance. So power in each element. And then, do a power balance. So for part A, which is this stuff, and B is the power balance. Part A, we're going to use this formula, V effective phasor, I effective phasor conjugate. This so V effective is the same as V RMS, which is given. So if we had I RMS, we could take the conjugate and get S, and then we could peel that apart and get P and Q out of that. So this conjugate thing, once again, it's sort of lost in the math why that's a conjugate, but you could go through all the derivations in the text and if you felt like it, but I prefer to take that on faith and just use it as a tool. So we're going to use mesh current here. Okay, so we need to establish some mesh currents. So we'll go, so there's this plus symbol. It doesn't really mean anything in this particular circuit. You'll see in the next chapter where this will have some significance. But for now, we can just choose any direction. You might as well agree with the plus like we've been doing in chapter 4. So we'll call this I1 mesh and go around the same direction and call this I2 mesh. And these are phasor mesh currents. So mesh current for I1, right, is going to be these three components, or sorry, these two components. Ohm's law across these things. Remember, mesh current is going to be VI terms and VZ, I equals V over R. Wait, we're doing, yeah. So, sorry about my little, yeah, we're summing voltages in a loop, so it's, IZ, sorry. I haven't had enough. Here, let me have a little bit of coffee real quick. All right. So IZ and then we might have a V term. So we have these IZ and then V here, right? IZ, V. So going around here, you're going to have the 10 minus J20. That's that's Z, I1 phasor. right? That's what I've been calling the primary terms, or the terms due to the primary loop here, the I1 loop. Then you got to use superposition, right? And the shared component, this capacitor here, is going to be it's going to be minus J20 I2, and then the impedance is negative, so I just wrote it in parentheses here, put the negative sign in parentheses, and then the sign on the term is going to be negative because these two loop directions disagree, so it's negative. And then you could add in this, because we're summing. If you wrote the V term here, you'd be coming in the negative terminal and it would be negative, but we're going to end up moving that to the other side where it's positive. So this is 170 angle 0. So sources equals loads is another way to look at this. This is my source and it adds up to these loads. Different ways to write these, whatever works for you. So I2 mesh current is, okay, this I2 is going through these three terms, so it's the 12, the 16, and the 20 has I2 phasor through them, right? Then the shared capacitor here is minus J20 I1 phasor, and then the currents disagree, so there's a negative sign, and those sum up to 0 angle 0 degrees volts. There's no voltage source in here, so it's just 0. Then, so we can rearrange this. So here, there's a solution here. There's two equations, two unknowns, two EQs, two unknowns. So there is a solution. Now that varies on your calculating device, your calculator, or whatever you use to get these guys crunched. But I'll work it a little bit further to show you how I do it in my calculator. So rearranging this stuff just to get it in standard form, rearranging the first equation, it's 10 minus J20 I1 plus 0 plus J20 I2 equals 170, is 170 plus J0. And the second equation becomes 0 minus J20 I1 plus something's wrong here. This is a positive. This J16 is positive here. So then it ends up being minus 4J I2. Had a messed up sign here. This is 0 plus J0. So I use a matrix in my ancient HP 28S, which I found an emulator for. Yeah, I left my calculator in my office and they won't let me back in my office. And I don't want to learn how to use a new calculator, so I found an emulator, but I haven't installed it yet. Anyway, so the matrix I1 over I2, or the 1 by 2 matrix, is given by these guys in a matrix. So it's 170 plus J0 over 0 plus J0 over these four coefficients, right? These four coefficients right here. So in this matrix, 10 minus J20, it's this first coefficient, and this second guy, 0 plus J20, and then this guy here is 0 minus J. What's a plus here? So minus. It's a plus. Is this plus 20? What's going on? Shoot. Negative, negative, plus. A couple of boo-boos. There might even be more. Now I'm getting worried. No, that's plus J20. 12 minus 4J. Hopefully that's all my things. Anyway, I set this up in my calculator, these matrices of complex numbers, and punch the divide button, and I get the answer comes out. 4 plus J1 amps for I1, and I2 is 3.5 minus J 5.5 amps. That's the I1 and I2 phasors. So we can go back to this thing and start working on the. Well, we're trying to find the. So this is ambiguous what they're asking here. This is, let's just say this is at the source. So there's at the source, we're going to do a power balance anyway and get everything, but let's do the source first. So there's this voltage and this current, right? So we can use this formula here for the power at the source. So, S at the, let's even just say that that's at the source. It's going to be V effective phasor, I effective phasor conjugate. So it's 170 plus J0. It's the voltage at the source. Here it is in polar, here it is in rectangular, and I'm using rectangular right here, times this guy conjugate, the I1 coming out of this thing, but we need the conjugate, so it's 4 minus J1. So punch that in your machine, and your machine will tell you that number right there. That's the answer to part A. Well, this is P, and this is Q. So P is 160, Q is 170. So that's all the three things they're asking for in part A. So before we go on, we can just say a couple of things. You can say at the source. So, all right, source is delivering, just to be explicit, delivering the real average power P equals 680 watts. All right, and the source is it's delivering 170 capacitive VARs, or you could say that it's absorbing 170 magnetizing VARs. So let's just say it's all three of those things. It's delivering Q equals 170 capacitive VARs. Or, yeah, that's right. Or you could say that the source is absorbing, use 170 magnetizing VARs. I don't like either of these, because it kind of doesn't even really matter. It's a sinusoid going back and forth, Q is just, yeah. It sums to 0, so it doesn't even really freaking matter. So I don't really like that too much, but anyway, it's good to play with this a little bit. So anyway, Q is negative. Just to line up this phasor here, this rectangular phasor with the phasor diagram. And this is Q. This is 170, negative 170. It's down. And there's an angle in here, which we didn't calculate, but we could if we wanted to. And then this is S on the hypotenuse. Okay. So that's what the source is doing. What about all of the loads? So part B is the loads. What are those guys doing, huh? So let's look at this 10 amp. We want to calculate the loads independently of all of these. This guy, this guy, this guy, and this guy, right? All of these four elements, and it should total up to the power being delivered by the source, right? Otherwise, you've discovered a new source of potential energy, and you're going to be a bazillionaire. But more likely, you just did something wrong. But if you do become a bazillionaire, don't forget about me. So the 10 ohm resistor is real power. So we're going to use this equation. We're going to use P is I effective I squared R. Okay, that's what we're given here. So you got to be careful when you're given these phasors or sinusoids. When you're given a source in the book, sometimes they give you peak value and sometimes they give you RMS value. They do that with phasors and they do that with cosine, time domain signals. So you just got to watch. So here they've already given you RMS, which is the same as effective. So we can calculate this guy out. So this guy it's going to be the magnitude of I1 squared times R, and this is where this is effective. This is RMS or effective. So if we had the magnitude of that, then we could do it. So I1 magnitude. Well, so I didn't take the time to do the polar form here. This is the rectangular form of I1. That's what I1 is going through this 10 ohm resistor, and this is the rectangular form. If you punched your rectangular form button, you would get the magnitude of this thing, but I didn't do that. But just to point out that, you can still use Pythagoras to get this guy. That's root 17 would be the value of the polar phasor. So it's just playing with some math and a little bit differently to work your brain out a little bit. So this is it's 170, and this is watts. Okay, so you're using RMS value, which is what we're originally given, and then we're calculating the magnitude of that from the rectangular phasor. We're really calculating the polar component, or the magnitude from the polar component. So that's that answer right there. So, likewise, we could do the power in the 12 ohm is, it's the magnitude of I squared. This magnitude, we're just showing some different notations and stuff. Why is it? Just to make you think that make you realize that it's this distance here that we're interested in here, right? This, the magnitude. Without drawing all the components out, they're just using this absolute value symbol just to make you work with the math a little bit, make it just a tad bit harder. So I2 magnitude, once again, we have the polar form. I'm sorry, the rectangular form of this guy. We could calculate that, the magnitude using Pythagoras. This ends up being root 42.5. So this guy is root 42.5 squared times 12 ohms. Works out to be 510 watts. Okay, now the cap and the inductor, these are reactive elements, reactive power Q. Okay, real power. The resistors are real power P, and the cap and inductor are reactive power Q. So here this dude, the reactive power in this guy, so we need the branch current, right? We need the branch current, which is I1 minus I2. We need the magnitude of the branch current going through this, right? It's I1 going down, I2 going up. So this is the branch, right? Branch current magnitude. So times the impedance of the cap. So we need these things. So I1 minus I2 is 4 plus J1, this thing, minus 3.5 minus J 5.5. It's 0.5 plus J 6.5, and its magnitude. Its magnitude is going to be by Pythagoras, 0.5 squared plus 6.5 squared. It's going to be root 42.5. So this is a total coincidence. Okay, I'm just going to write coincidence. Coincidence that this value is the same as the value in the 12 ohm resistor. It's the way the numbers worked out. It has no meaning beyond just luck. So we can crunch this dude as 42.5 root. That's I1 minus 2 magnitude. And square that and multiply it times the impedance of the cap, which is minus J20, and you end up with minus J850, and the units are going to be volt amperes reactive, or VAR. Right? That's the impedance. That's the impedance in this guy. We need the impedance in this guy. That's the last dude. So this is Q in the J16. This is going to be the current through it, which is magnitude of, it's I2 that's going through there. We want the magnitude of that squared. You realize we're just using I squared R sort of, but little variations to account for the fact that it's phasors times the impedance of the inductor. So this guy so we already calculated this guy out. It's over here. So it's 42.5 root 2, square root, quantity squared, times J16, the impedance of the inductor. So it's it works out to J680 var. Okay, where's our 770, 510, J50? Do these balance? They should, or we messed up. So this is what, you ever heard the expression, mind your P's and Q's? Well, this has nothing to do with what we're talking about, but at least that's not where the expression comes from. But anyway, so what are these? What's the sum of these dudes? It's going to be 170 plus 510 plus minus J850 plus J680. So 170 plus 510 minus J850 plus J680, and so this guy sums to 680, and these two guys sum to minus 170 J, and bingo, that's the source, right? This equals the source. So yay, or yeah, I don't know how to spell yay. Anyway, power balance, mesh current method. End up with the simultaneous equations with complex numbers in them. There's a branch current in here, and which is the sum of these mesh currents. There's this funny variation on I squared R, where you need to use RMS, and we had to calculate the magnitude of these currents from their rectangular format using Pythagoras. That's about it.